Am I audible to you all?
Yes, ma'am.
Okay. So let's start with the session number 44 of module 5, that is the design of columns and footings. So we are dealing with the design of columns. In the previous session, we have discussed regarding the design of columns which are axially loaded. So in today's session, we'll continue with the design of axially loaded columns along with axially loaded and uniaxial bending columns. So first we'll continue with the axially loaded columns, then we'll proceed with the columns which are acted upon by axial load as well as the uniaxial moment. So let's start with the today's session with this numerical example. So all of you take down, simultaneously try to solve this numerical so that you'll be having a better idea of how to solve or how to design for the column section. Design the reinforcement in a column of size 450 mm by 600 mm subjected to an axial load of 2000 kN under service dead and live loads. The column has an unsupported length of 3 meter and its ends are held in position but not in direction. Use M20 grade concrete and Fe415 steel. So before we start up with anything, let's make note of the things which are being given and what can we calculate from that data. So we are supposed to design the reinforcement. That means we need to calculate the value of ASC. Make sure of it. Then the size of the column is given. It is a rectangular column, that is 450 mm by 600 mm. So here B value we are going to consider it as 450 mm, D value as 600 mm. And it is subjected to an axial load of 2000 kilonewton. So P value is given as 2000 kilonewton. Remember, P value is given to you, not the PU value. Next one, the column has an unsupported length of 3 meter. Unsupported length of 3 meter and its ends are held in position but not in direction. The ends are held in position but not in direction. If they are held in position but not in direction, now length is given, effective length we need to find out. In order to find out effective length, let's go through IS 456. Here, third category, that is the column is held in position at both the ends but not restrained against rotation. This is the same case which they have given in the example. So for that case, we are supposed to consider the effective length as 1L. So the coefficient is 1. So LEX is equal to LEY, that is equal to 3000 mm square. mm. Now we need to check whether it is a short column or the slender column, because the design for the short column is different than that of slender column. So before we start up with the design, we need to check whether it is a short column or whether it is a slender column. So in order to check for that, what we'll do, we are going to calculate LEX by D ratio and LEY by B ratio. So LEX by D, that is 3000 divided by 600, D value. This value is also less than 12 and LEY by B is also less than 12. If LEX by D and LEY by B, if they are less than 12, then we can classify the column as short column. We can classify the column as short column. Otherwise, if the value is more than 12, then we would have classified it as a slender column or the long column. Now, once we are done with the check for the shortness, that is whether it is short column or the long column, once we have checked for it, next thing is to check for the minimum eccentricity. To check for the minimum eccentricity. So In order to check for the minimum eccentricity, we use the equation here. E minimum is equal to, in the x direction, LEX divided by 500 plus D divided by 30. And substituting the values, we get it as 26 mm. And we need to compare 26 mm and 20 mm. So out of these two values, 26 mm is greater. So we are going to compare this 26 mm with the minimum eccentricity. So that is 0.05 times D. 0.05 times D refers to as 0.05 into 600, that is equal to 30 mm. That is equal to 30 mm. So once we get this value, 26 mm is less than 30 mm. Hence, we can say that the eccentricity is okay. Whatever the eccentricity we have calculated, that is less than the minimum value, that is 0.05 D. So in the direction of shorter length, now it is for the longer direction. Now for the shorter direction, the same equation we are going to use. Only the thing, in place of D, we are going to substitute it as B value. E minimum in y direction is equal to LEY, that is effective length in y direction, divided by 500 plus B divided by 30. So we are getting 21, and we are going to compare 21 and 20 mm. So 21 is higher. So now let's compare 21 mm with 0.05 times B value, that is 22.5. So this value is less than or greater than the E minimum. So we can say that the eccentricity is okay, or we can say that the minimum eccentricities are within the limits, and hence the code formula for axially loaded column can be used. So now the minimum eccentricities satisfy the given criteria. So now let's use the equation in order to find out the amount of steel. That is, Pu is equal to 0.4 FCK into AC plus 0.67 Fy into ASC. Now here in the example, Pu value is not given to us. Here in the example, Pu value is not given, we are given with P value. So we can convert P, that is working load, into factored load. So 2000 into 1.5, that is equal to 3000 kilonewton. 3000 kilonewton. Now the design of longitudinal reinforcement, we can do it as Pu is equal to 0.4 as it is, FCK value is given to us, area of concrete. Area of concrete. Here, area of steel and area of concrete, they are not known to us. Area of steel and area of concrete, they are not known to us. If they are not known, what we can do is, we know the gross area. We know the gross area. Here, let me show you. As we have discussed this in the previous session, gross area, that is AG, is equal to length, or B into D. B into D. And we are going to assume the value of gross area, the percentage of steel. Here we are going to assume the value of percentage of steel. So how to assume the percentage of steel? As we have done it in the previous sessions, we are going to assume the percentage. Here, what will assume? ASC, that is amount of longitudinal steel, is equal to 1% of the gross area. 1% of the gross area, that is ASC is equal to 1% of gross area. So what we can write? The area of concrete. Area of concrete. We know that gross area is ASC plus AC, that is area of steel plus area of concrete. If 1% of the gross area is ASC, then 99% will be the area of concrete, that is 0.99 into gross area. So this is how we need to substitute, and ASC value we are going to substitute it in terms of gross area, or AC value we can substitute it in terms of gross area, and only the unknown will be ASC. So that ASC we can substitute as 3111 mm square. After substitution, what we can do, we can calculate ASC value, and in view of the column dimensions, that is 450 mm by 600 mm. Here, let me use it. Now, if this is the column, here what we can write, we can say that at the corners at least we are going to provide 4 columns or 4 reinforcements. 4 reinforcement bars, they are to be provided at the corners, and by seeing this, here you are supposed to provide 4 more at the centers. By seeing this, you can say that there should be 4 more bars at the corners. So what we can do is, here in view of the column dimension, that is the larger column dimensions, it is necessary to place intermediate bars in addition to 4 corner bars. These are corner bars. In addition to these 4 corner bars, we need to provide 4 more intermediate bars at the center. Now, once we need to provide that, so find out the diameter and the number of bars in such a way that in total it should provide at least 3111 mm square. That is 4 bars of 25 mm diameter at the corner and 4 bars of 20 mm diameter at the center. So that turns out to be ASC provided 1964 plus 1256, that is 3220, and this ASC value is more than what is required. So hence we can say that it is more than the required value. Now once we provide this ASC value, we need to check whether this provided value is within the limits or no. So percentage of steel is equal to 100 AST provided divided by B into D. So that is turns out to be 1.192, and this 1.192 is within the limits, that is within 0.8, greater than 0.8% and less than 6%. Hence we can say that the steel provided is okay, because as we have discussed in the previous sessions, the steel provided should be within the limits of 0.8% to 6%. So 1.192 is more than 0.8 and less than 6. Now coming on to the design of transfer steel. Design of transfer steel, that is diameter of tie. Diameter of tie is equal to 1/4 of diameter of main steel. So diameter of main steel is 25 mm. Out of 20 mm and 25 mm, whichever is the highest diameter, that we need to consider. So 25 by 4, that is 6.25 or 6 mm, whichever is greater. So here we need to consider 6.25, and we can provide a diameter of 8 mm. Here make a correction, it should be 8 mm. Provide 8 mm diameter lateral tie. 8 mm diameter lateral ties are to be provided. Now the spacing we need to consider. Spacing, that is 300 mm or 16 times the least value of the longitudinal bar 16 times 20, or least lateral dimension, that is 450. Out of 450 and 600, whichever is the least value, that we need to consider. So out of these three values, 600 is the minimum. Then we can say that provide lateral ties of 8 mm at a spacing of 300 mm center to center. Provide lateral ties of 8 mm diameter at a spacing of 300 mm center to center. Now, next thing is we need to proceed with the detailing of the column. Detailing of the column. This is the cross-sectional detail of the column. The column is of dimension 600 mm by 450 mm. Column dimension is 600 mm by 450 mm. Now, out of this column, we are supposed to provide 4 bars at the corners, and those are of diameter 25 mm, and the intermediate bars, which are 4 in number, those are having a diameter of 20 mm. Here the lateral tie is to be placed one for the exterior bars, and for the intermediate bars there should be one more lateral tie to be provided, and clear cover of 40 mm is to be provided. Now, with this, we shall end up with the design of axially loaded column. So, similar way you can design it for circular column, square column, and so on. So, we shall end up with the design of axially loaded column. Now, let's proceed with column with axial load and uniaxial belting. Column with axial load and uniaxial bending. So how to design such kind of columns? Now, in order to design such kind of columns, along with IS 456, we need one more parameter or one more code book, that we call it as SP16. That we call it as SP16. This is SP16, and it is also called as a design aid to IS 456 1978. Either SP16 or design aid to IS 456 1978. Here you have all the parameters, even whatever the designs you have done using IS 456, that is design of beams, slabs and all, those designs can be easily done using SP16. Here there are many charts, many graphs, so based upon which you are going to get the value of flexural strength or any other parameter. So here for the flexural members, the design is given, that is beam and slabs especially, those are coming under flexural members. And compression members, compression members are nothing but the columns. These clauses we are going to use it for our design of columns. And page number 99. So these charts are very important. Here for the compression members, you are going to refer only this parameter or this portion of SP16, because for your syllabus only design of columns is to be done using SP16, not any other structural member. Here it is been noted, given here, see, axially loaded compression members, that means the axially loaded columns. Here E minimum, how to calculate E minimum, that equation is given, L by 500 plus D by 30. Then even the PU equation is given, PU is equal to 0.4 FCK AC plus 0.67 FY into ASC. So that is being given. Then the value for or the design of combined axial load and uniaxial bending is given. Combined axial load and uniaxial bending. So it depends upon whether we are providing the reinforcement on one side or we are providing on reinforcement on both the sides. Here the reinforcement is provided on both the sides, all the 4 sides. And so depending upon the type of that column, then we need to proceed with the design. So here there are few design examples also, you can refer for those design examples. So this is axial compression, we are not going to refer for this. Yes, here it is being mentioned compression with bending, that is the column with uniaxial bending, and the reinforcement is distributed equally on two sides. Here you can see the reinforcement type. For the column, reinforcement is provided on only two sides. So if reinforcement is provided on two sides, and what is the grade of steel, and what is the ratio of d dash by d, all these parameters decide which chart has to be used. Here chart 27 will be used only if we have grade of steel as 250 Newton per mm square, d dash by d value as 0.05, and we have reinforcement on only two sides. This is how we can proceed with. So once we start with the design, we are going to refer. Okay, let's start with a numerical example now. Determine the reinforcement to be provided in a square column subjected to uniaxial bending with the following data. Size of the column is 450 mm by 450 mm. It is a square column. Concrete mix is M25. Characteristic strength of steel is 415 Newton per mm square. Factored load, that is PU value, is 2500 kilonewton, and factored moment is 200 kilonewton meter. Arrangement of reinforcement on two sides, on four sides. Assume the moment due to minimum eccentricity to be less than the actual moment, assuming 25 mm bars with 40 mm cover. 25 mm bars and 40 mm cover. So now we need to find out the value of D. Value of D. Here 40 mm cover is given. So value of D is nothing but 40 mm plus 12.5, that is half of the diameter. Half of the diameter is equal to 52.5 mm. So D dash value is nothing but clear cover plus half of the diameter of the main reinforcement. So D dash divided by D value is 0.12. 0.12. And this 0.12 is more than 0.1 and less than 0.15. More than 0.1 and less than 0.15. If it is more than 0.1, we can refer to directly the charts for D dash by D value equal to 0.15. D dash by D value equal to 0.15. Here D dash by D value 0.1 is there. D dash by D 0.15 is there. And let me check what is the grade of the steel. Grade of steel is 415. Grade of steel is 415. So what I'll do, I'll be searching for grade of steel equal to 415. It is 250. Here again it is 415, but D dash by D is 0.05. 415.1. 415 and D dash by D is 0.15. So we need to refer to chart 33 for the calculation part. The reinforcement is on only two sides. Steel grade is 415 and D dash by D value is 0.15. So with this parameter, now I want the value of mu by FCK BD square and PU by FCK BD. So that if I know these two values, I am going to intersect or make these two values intersect at particular point and assume the value of P by FCK for that particular respective curve. Now for the reinforcement on two sides, referring to chart 33, PU by FCK BD. PU by FCK BD. PU value is given, FCK B into D. PU value has to be converted to kilonewton to Newton. So it is 0.494 and mu by FCK BD square. Mu is nothing but 200 kilonewton meter. Both the factored values are given, need not multiply with the partial safety factor. So 200 into 10 to the power of 6 divided by FCK B into D square. So it is 0.088. So 0.9449 and 0.088. 0.49 is there. So this is PU by FCKBD. PU by FCKBD is 0.49. 49 refers to somewhere here, near to 0.5. Near to zero point 0.5 and 0.088. 0.088 is 0.09. 0.09 is somewhere here. So let us project it upwards and in the horizontal direction. So somewhere it comes around this point in between these two curves. In between these two curves, that is 0.08 and 0.1. The curves come between 0.08 and 0.1. If it is 0.08 and 0.1, then we can say that the value of P by FCK is in between 0.08 and 0.1. So that is, we have considered it here as 0.09. 0.09. So if this is 0.09, we know the value of FCK, so we can find out the P value, that is 0.09 into FCK, that is 2.25%. And this 2.25%, using this value we are going to find out the amount of steel, that is P is equal to 100 AST divided by BD. So interchange the values. P is equal to 100 AST or ASC here divided by B into D. Now percentage of steel is known, B is known, D is known. We can find out ASC value, that is PBD divided by 100. PBD divided by 100 gives us 4556 mm square. Now if we are finding out the reinforcement on four sides, then we need to proceed with the other charts. Here this is on two sides. So keep on checking. Yes, reinforcement equally distributed on four sides. Fy is 250. No, Fy we want 415. So Fy is 415. Yes, Fy is 415, but D dash by D value is 0.05, but we want 0.15. Yes, we can refer here. Fy is 415 Newton per mm square. D dash by D is 0.15 and the reinforcement is provided on all the four sides. Now for this, PU by FCKBD and MU by FCKBD square, their values are already calculated and we can find out P by FCK value. We can find out P by FCK. 0.088, it is almost here. 109 and it is almost 0.5. So the value lies between 0.8 and 0.1. 0.8 and 0.1. If it lies between 0.8 and 0.1, we can write it as 0.1, very near to 0.1. So P by FCK value is 0.1. Even you can take it as 0.095. So it is very near, so we are considering it as 0.1. So percentage of steel is equal to 0.1 into 25, so that is 2.5%. Now we can find out as here, that is amount of steel, longitudinal steel is equal to 5063 mm square. 5063 mm square. So this is how we are supposed to design for the column width axial load and uniaxial moment. And even sometimes if they are asking you to find out the number of bars and all, you can find it out. Here the diameter of bars is also already given as 25 bars. So using 25 bars, how many bars you can provide for two sides, that you can calculate. This is a rectangular column. Here we can say that the bars are to be provided on two sides like this. So how many bars we can find out? What is the total steel for two sides? That is 4, 5, 5, 6. If this is total amount of steel, the number of bars we can find it out as here we can find out the number of bars as AST or ASC divided by area of one bar, that is pi by 4 into 25 square. Pi by 4 into 25 square. So for this 25 square bars, how many bars are required? That we can calculate and put it in as the detailing. And then coming on to on four sides. If it is on four sides, we can provide two more bars here, and we can usually calculate ASC divided by pi by 4 into d square. This is how we need to calculate the number of bars required for the reinforcement. So in the next session, we are going to continue with the column loaded with axial load as well as uniaxial bending for the circular column. Now we have done it for the square column and the rectangle column. So we are going to continue with the circular column in the next session. So hope this numerical is clear for you all. Yes, everyone. Is this clear?
Yes, ma'am.
Okay, that's all for today. Thank you.